So today what we'll do is we will look at algorithms that learn the parameters of a Bayesian network given its structure using the maximum likelihood estimation approach under the assumption that the data is partially observed. Last class we saw that parameter estimation in presence of partially observed data or POD is challenging. And the reason for this being a challenging task is that the likelihood is no longer unimodal and it's no longer decomposable because we have this ugly term inside the likelihood, which is sum over all the variables that are not observed. Okay, so if you are given, let's say, a data set in which variables, let's say x1, x2, x3 are always observed, and let's say variables h1, h2, h3 are not observed, then likelihood is always defined over the variables that are observed. So what you want to do is, if you want to figure out the likelihood of any data point, let's say the data point is x1 equals small x1, x2 equals small x2, and x3 equals small x3, then this is nothing but, since the probabilistic model is defined over x1, x2, x3 and h1, h2, h3, to compute its probability according to the probabilistic model, we'll have to sum out h1, h2 and h3 from the joint distribution over x1, x2, x3 and h1, h2, h3. Okay, so because of this ugly term in the likelihood function, which is a summation over all the unobserved variables, we saw last class that the likelihood is not unimodal and it's not decomposable. Okay, as a result, unlike the fully observed data case or the FOD case, we are not going to get a closed form solution. So what we're going to do today is we are going to look at algorithms which use an iterative approach, okay, to solve this problem. Specifically, what we are going to do is we are going to look at two classes of algorithms. The first class of algorithm is called the expectation maximization algorithm. Also known as the EM algorithm, where E stands for expectation and M stands for maximization. And the second class of algorithms that we are going to look at is the gradient descent approach. Or in this case, since we are maximizing, it's called the gradient ascent approach. Okay, we are maximizing the likelihood, therefore it's called gradient descent. If the approach is used to solve minimization problems, it's called a gradient descent approach. Okay. So let's look at the first approach called the expectation maximization approach, or the EM algorithm. And what I'm going to do is, as I've done before, present the algorithm first, and then what we are going to do is we will analyze the algorithm, okay, and look at its properties, including its complexity. Okay. So let's start describing the algorithm. Okay, the algorithm works as follows. As I said, this is an iterative approach. So what we do is we start with a random setting of parameters. What I mean by that is, let's say you have parameters something like p of x1 is nothing but theta 1, and let's say p of x2 given x1 is nothing but theta of 2 given 0, and let's say theta of 2 given 1. Then you will initialize all of these parameters randomly. An example is, let's say you draw numbers out of a hat, and let's say this one is 0.2, theta of 2 given 0 is 0.3, and theta of 2 given 1 is, let's say, 0.73. Okay, so initialize the parameters randomly to begin the algorithm, and then you repeat the following two steps until convergence. In step 1, which is called the expectation step, you complete each incomplete example. Okay, so remember, we are in the partially observed data case. So we take each partially observed example and complete the example using the current parameters. Okay? So once you have completed each example in multiple ways, what you have essentially is a fully observed data. Okay? So you've taken your partially observed data set and it's essentially converted into a fully observed data set after you're done with step 1. Okay? After that, what you do is you update the parameters based on the completed data. And this is called the M step. How do you update the parameters based on the completed data? You essentially use the F4E solution. Remember, our F4E solution was a closed form solution. Right? So our F4E case was closed form solution. Okay? So we use that closed form solution to update the parameters. Okay? Now, based on these parameters, we go back to step 1, complete the data using the current model. Okay? And then in step 2 again, we update the parameters. So we keep on alternating between this E step, which is completing the data, and M step, which is updating the parameters until convergence. And by convergence, I mean that the parameters will not change, okay, for any future iterations. So this is the EM algorithm in a nutshell. So what we are going to do next is demonstrate the expectation maximization algorithm using an example given on the slide. You're given a Bayesian network having 4 variables A, B, C, and D, and we'll assume that each variable, the domain of each variable is the set true, false, where small a, let's say, denotes the value assignment of A to true, and A bar denotes the value assignment of A to false. Similarly, we have B and B bar, C and C bar, and D and D bar. Okay. The parameters of the model are denoted by the letter theta. The CPT at A is associated with just one parameter, theta sub A. Why just one parameter, you may ask? Okay, when the CPT of A has 2 values, one for A equals true and one for A equals false. This is because, and we have discussed this numerous times, the probability of A equals false can be computed from the probability of A equals true. Okay, so P of A equals false is nothing but 1 minus P of A equals true, which is the same thing as saying that this is nothing but 1 minus theta of A. Okay? Therefore, A is associated with just one parameter, theta A. B is associated with just one parameter, theta B. C is associated with 4 parameters because C has 2 parents, A and B, and therefore C will have, the CPT of C will have 8 values, and we can represent it using 4 parameters, one for each combination of A and B. So there are 4 combinations of A and B, and that's why we have 4 parameters associated with C. Similarly, the CPT at D will have 2 parameters, since it has only one parent. Each step, what we do is we first complete each partially observed example in all possible ways, and then for each completed example, we compute how likely that example is according to the current set of parameters. Okay? The effect of this step is that the data is now bigger and weighted. And in the M step, if you remember, we are going to do parameter estimation based on this weighted and much larger data set. Okay? To demonstrate this, what I'm going to do is I'm going to use an example or a data instance. Okay, so let's say A question mark D bar is the data instance, and in the first step what we will do is we'll complete the data instance in all possible ways. So since B, the values of B and C are unknown, the 4 possible completions of the data set or the data instance I should say are A, B, C, D bar, right? B, C bar, which is another completion, then B bar C, which is the third completion, and B bar C bar, which is the final completion. Okay, so the data point, since it has missing values for B and C, can be completed in 4 ways. Okay, so once we have figured out the completions, we will compute how likely each completed example is. Okay, and that will be the weight associated with that example. So how likely is this completion? The likelihood of that completion is nothing but P of BC given A comma D bar, right? A and D bar is known. Similarly, the weight associated with the second point is B comma C bar given A comma D bar. Okay, the third point will be P of A B bar given C. I made a mistake, so this is nothing but P of B bar C given A comma D bar, and the final point completion is B bar C bar given A comma D bar. Okay, so this can be computed using any inference algorithm. So for the example given on the slide, you can verify that the likelihood of the first completion is 0.0492, the likelihood of the second completion is 0.8852, third completion is 0.0164, and the last one is given on the slide. Now suppose you are given another example, let's say question mark BCD, which means that the value of A is missing while the value of BCD is known. Okay, so you do the same thing for that example. You complete the example in all possible ways, which is 2 in this case, because A can be true or A can be false, and then you compute the weight of those examples. So for instance, the weight of the first completed example is nothing but P of A given BCD, and the weight of the second example is P of A bar given BCD. Okay, so if you have a data set, let's say having n examples, and let's say there are exactly p variables missing in each example. Okay, so p variables have missing values in each example, then how many possible completions are there? Think about it, right? So each example can now be completed in 2 to the power p ways, assuming that each variable takes 2 values. And since there are n examples, the total number of examples, completed examples I should say, will be 2 to the power p times n. Okay, and remember, all of the completed examples will be weighted by the appropriate weight. So to summarize, the output of the E step will be a bigger data set, and not only a bigger data set, but a weighted data set. And now let's see what happens in the M step. So in the M step, what you do is you update the parameters of the model based on the bigger and weighted data set. Okay, so for our running example, if you remember, we had 2 partially observed data points. The first one was A question mark D bar, and the second partially observed point was question mark BCD. Okay, so these are the completions of the second point, and the first 4 are the completions of the first point. Okay, so now that you're given this bigger and weighted data set, you can update the parameters in the M step. So how do I update the parameter theta A, for instance? All you have to do is just compute the sum of weights of all points where A is true divided by the sum of weights of all points. Okay, So the sum of weights of points where A is true is 0.0492. So I have it there. The second point as A is equals true, so I'm going to count that weight. The third point as A equals true, so I'm going to count that weight. The fourth point as A equals true, and so on, I'll count that weight. The fifth point also has A equals true, so I'll count that weight. But the sixth point does not have A equals true. Okay, so I won't count that weight. So the numerator is nothing but the sum over the weights of all points where A is true, and the denominator is where the sum is computed over all points in the model. Okay? So that gives us 1.4878 divided by 2, and so the updated value of theta A will be 0.7439. So if you remember, we started with a model that had theta A equals 0.3, and now we will get theta A equals to 0.7439 after the M step is complete. Okay, so after the M step is complete, we will get a set of updated parameters. Okay, then what we do in the E step is we compute these weights again, but these weights will change, right? Why will these weights change? These weights will change because our parameters have been updated. Remember, like, these weights were computed using the current set of parameters. Okay, so we'll get a new set of weights, and based on those new set of weights, we'll update the parameters again, and from the updated parameters again, in the third iteration, we will have another set of weights, and so on and on and on until the algorithm converges. Okay, so that's the expectation maximization algorithm. Now let us come to our favorite part, where we discuss the time and space complexity of the algorithm we just presented. As we saw, given n incomplete examples, and assuming that each example has p missing values, so p variables are missing in each example, let's say, we'll have to compute at least n, or compute the weights of at least n times 2 to the power p examples. Okay, which means that the time complexity will be bounded by n times 2 to the power p. If p is large, then this algorithm is clearly impractical. For example, if there are 50 missing variables in the problem, or 50 hidden variables, or 50 latent variables, then EM will be impractical. The good news is that we can often improve the time complexity of the EM algorithm by computing expected sufficient statistics for each parameter, okay, which are given in the equation on the slide. So let us say that you want to compute the expected sufficient statistic of the parameter x given u, right? So theta of x given u, which is nothing but the parameter associated with the CPT of variable x given an assignment u equals bold U to the parents of x. Okay, so it turns out that the expected sufficient statistic for theta of x given u is nothing but the sum weight of x comma u divided by the sum weight of u. Okay, and the weight of x given u for each data point is equal to the probability of the joint assignment x and u given the data point oj. Okay, similarly, the weight of u is nothing but the probability of u given the data point oj. Okay, so if you recall, in the unweighted case, when the data set was unweighted, the sufficient statistic was the counts of x comma u divided by the counts of u. Okay, so in the EM case, the expected sufficient statistic is nothing but the sum over the probability of x comma u for each example divided by the sum over the probability of U for each example. Okay, so what this means is that if we somehow compute the expected statistic for each example and store it, and actually technically we don't need to store it because uh, we can have a running sum. So, but let's say we can compute the expected statistics for each example, then the complexity will no longer be bounded by n times 2 to the power p, but the complexity will be bounded by n times inf, where inf is the time complexity or the space complexity of the inference scheme that is being used. Okay, so why is this important? This is important because now the complexity is no longer exponential in the number of missing variables, but the complexity is now just linear in the time complexity required by the inference procedure. Okay? So if it turns out that given the observations, right, or given evidence, the tree width of the remaining variables, right, and the remaining variables are nothing but these p variables, is bounded by some constant, let's say w, and the complexity of inference will be just exponential of w rather than exponential in p. And we know that w is often smaller than p. For instance, if the tree width is 1, which means that given the observation, the tree width over the Bayesian network, over the remaining Bayesian network is 1, okay, then this step is a linear step. Why? Because the complexity will be O of n times exponential in 1, which is equal to O of n times p, right? So if you remember, like, the overall complexity will be p times exponential in 1 for computing the statistics. Okay, so the overall complexity now becomes linear in p rather than exponential in p. So having discussed the EM algorithm, what I want you to do is read the precise algorithm given in the book Kohler and Friedman. Okay, and try to understand the procedure and try to analyze its time and space complexity. Under the assumption that you are using the junction tree algorithm as your inference procedure. Okay, so the EM algorithm is given in essentially two steps or two sub-algorithms. The first one is computing ESS, which is computing the expected sufficient statistics, and then the second step is the actual iterative algorithm, the expectation maximization algorithm. Okay, so I'm not going to go over the details of this algorithm, but what you can do is you can go home, and in this case actually you're already home, but try to read this algorithm, okay, and try to understand the way. So finally what we'll do is we'll look at some important properties of the EM algorithm and summarize what we just discussed. The most important property of the algorithm is that at each iteration of the algorithm, right, so each iteration is nothing but the E plus the M step. At each iteration, the likelihood can only increase and it will never decrease. Okay? As a consequence of this, EM will often converge to local maximas. Okay? So that's the good news. The bad news is that EM will converge to different parameters with different likelihoods depending on the initialization that is being used, right? So the initial parameters that you start with will dictate what kind of solution you reach. If you recall, our likelihood function was multimodal, right? So it was something like that, right? What these two properties mean is that if I start with an initialization that is that point, I'll reach a local minima, which is that guy, right? So on the x-axis I have theta, and on the y-axis I have the log likelihood of theta, let's say. Okay. If I start the EM algorithm using this initialization, I'll reach that local maxima. If I start the EM algorithm over here, I'll reach that local maxima, which is worse than our previous local maxima. Okay. And if I start the EM algorithm over there, I'll reach a local maxima, which is also the global maxima. Okay. So this is the solution that we want to reach. Unfortunately, EM will only reach this global maxima if we start anywhere here or there. Okay? If we start anywhere else with our initialization, then we will reach other local maximas. The final 2 points I want to make is that each iteration of the EM algorithm will perform, or I should say in each iteration of the EM algorithm, we will have to perform inference on the Bayesian network. Okay? And the sufficient statistics that we'll have to compute while performing inference are the posterior probabilities over all the parameters in the Bayesian network. Okay? So this is a hard task. This is a hard task because unless the tree width of the graphical model is small or the graphical model has like other properties, inference will often be exponential in general. As a result, in practice, in order to compute these sufficient statistics or these so-called or these posterior probabilities, we'll have to use approximate inference algorithms such as IGGP or sampling algorithms. Okay? Therefore, in practice, and this is an unfortunate situation, we won't have convergence guarantees to local maxima of the likelihood function because we cannot compute the likelihood exactly. So that concludes our discussion of the EM algorithm. On Tuesday, we will I'll try to answer questions about this algorithm. We will also have a homework which will be assigned in the next few days on implementing the EM algorithm. But I'll not have you implement the junction tree algorithm. So you'll implement the naive version of the EM algorithm, which has a complexity bound of n times 2 to the power p. Okay, so I will make sure that this algorithm is doable in the sense that I'll make sure that the number of missing variables is bounded by 4 to 5, right, and not more than 5. Next, what we will do is we will look at the gradient ascent algorithm for solving our parameter estimation problems in the presence of partially observed data set. Okay, so the gradient ascent algorithm is a generic procedure for solving optimization problems of the form max x f of x, right? The only requirement here is that, so here x is, you can think of them as your parameters, and you want to find a setting of the parameters such that the objective function f of x is maximized, okay? So the only requirement here is that the function f of x should be differentiable. And if it is differentiable, then you can use the gradient ascent procedure to find the local maximas and in some cases global maximas of the function. Okay. The idea is fairly simple. What you do is you compute the gradients and move the parameters in the direction of the gradient. Okay. Let me describe the algorithm to you. The algorithm takes as input a initial starting point, which is the same as the EM algorithm. So you initialize all the parameters randomly. The objective function f sub obj that needs to be optimized, and a convergence threshold delta. So if the difference between the current solution and the old solution is less than or equal to delta, then you stop the algorithm. So there are two main steps in the algorithm. You start the iteration count at 1, and then at each iteration you update your parameters, right, which are, let's say, theta t, by adding eta times the gradient of the objective function at the point theta t. Okay, so theta t plus 1 is nothing but theta t plus eta times the gradient. Okay, and you keep on updating the gradient until, as I said before, the difference between the current solution, which is theta t, and the previous solution, which is theta t minus 1, is less than or equal to delta, which means that the solution did not change much. And at the conclusion, what you do is you return the so-called converged value for the parameters theta. So what I'm going to do is I'm going to demonstrate how this algorithm works for a simple function that I plotted here, right? And I believe that the function is nothing but f of x is equal to minus 4x squared. Okay, so we know that the global optima of the function is at 0. Okay, and what we want to do is use the gradient ascent algorithm to find this 0. So as I said, what the algorithm does is you begin at some randomly chosen starting point, and let's say that's our starting point, and then move this parameter. So this is a single dimensional problem in this case, so we only have one parameter, x, okay, that we want to change, and we know that the optimal solution is at x equals 0. Okay, so we want to change that parameter. What we are going to do is we are going to take the gradient of this function at that point. So the gradient is nothing but the tangent, right? Slope of the line that is tangent to that function. So what is the slope of this line? The slope of this line is going to be positive, right? So since the slope of this line is going to be positive, what I'm going to do is I'm going to take my x and add to it some number. Okay, and that number is nothing but eta times the gradient of the objective. Okay, so since the gradient is positive, because the slope of this line is positive, I will move in this direction, which is towards the optimum. Okay, so let's say instead of starting at that point, had you started at this point, what will happen in that case? In that case, if I draw a tangent to this, the slope of the tangent is negative. Okay, so let's say if I started at something like a 1.0, what would have happened is that I would have subtracted some number from 1.0, okay, because the slope is negative. So x plus eta times some negative quantity will be x minus some negative quantity, right? So x will decrease. Okay, what I mean by that is you're going to move to the optimum, which is 0 in that case, in this case. Okay, so this is how the algorithm works. You are at a certain point, you compute the gradient of the function, of the objective function at that point, and move in the direction of the gradient. Okay, so eta is called the learning rate, and it dictates how fast or how slow the algorithm converges. As you can imagine, if the learning rate is very small, you are going to take baby steps towards the optimal solution. Okay, so you're going to take like really baby steps and reach the optimal solution. If eta is very large, technically you can reach the optimal solution very quickly. Unfortunately, if eta is very large, the algorithm actually may fail to converge or even diverge. So for instance, let's say you started at that point. If eta is very large, okay, and you move in the direction of the gradient, so let me just erase these drawings. If you remember, the gradient was positive at that point, and if I set my eta to too large, what I might do is, instead of reaching a solution which is over there, or I should say reaching another point x which is over there, I might diverge and actually reach a point which is somewhere over there. Okay, and again the gradient is going to be positive, or I should say negative at this point, and if my eta is too large, I might actually end up there, and I might keep on continuing this process, and instead of actually converging to the optima, I might actually diverge away from the optima. Okay, so eta is very important. Eta is the learning rate, and typically what people will do is set the eta value to a very small value, so that they are guaranteed at least to converge to the optima rather than going away from the optima. So this is a generic algorithm, and as you might imagine, there has been decades and decades of research work on this. And so the good news is that you never actually have to implement this algorithm in practice. What you can do is, there are scores of libraries out there, and what the libraries need is for you to just specify what the derivative is, right, or what the gradient is in this case, and as well as the objective function. So give an equation for the objective function and give an equation for the gradient, and you're all set, right? The library, right, for gradient ascent or gradient descent will do the magic for you and find the optimas. Okay, I will demonstrate the gradient ascent algorithm using our example Bayesian network. So one thing that we want to keep in mind is the main task in the gradient ascent algorithm is computing the gradient. So once you compute the expression for the gradient, you're all set, right? All you're going to do is you're going to take that expression and substitute the value of the current parameters in that expression. Okay, and once you do that, you have the value of the gradient, and you change your current solution by adding eta times the gradient to the current solution until the so-called local maxima is reached. Okay, so so this algorithm, same as the EM algorithm, does not find global maxima. It's susceptible to initialization. So depending on the starting point, you will reach a particular local maxima. The local maxima may be the same as the global maxima, but the likelihood of that is very low. Okay, so our objective function here is nothing but the log likelihood score, and so what we need to do is find an expression for the derivative of the log likelihood with respect to each one of these parameters theta. Okay, so I want the derivative of the log likelihood with respect to theta A, derivative of log likelihood with respect to theta B, and so on and on and on. Okay, so what I'm going to do on this slide is use a data instance, which is the same data instance as before, and write down the expression for the log likelihood with respect to the data instance. Okay, so if you remember, our log likelihood was nothing but sum over I is equal to 1 to n, where n is the number of examples, log of p of the example, the probability of the example, according to the current setting of parameters theta. Okay, so that's why we said that log likelihood is nothing but dependent on the parameters theta as well as the data set. So for the purpose of discussion, let's assume that we just have one data point, and so let me write down the log likelihood with respect to this data point. So log likelihood here is log of P of A comma D bar with respect to the current set of parameters theta. Okay, so this is nothing but log of sum over B and C, P of A comma B comma C D bar theta. Okay, so since B can take two values and C can take two values, this expression or the summation is over four values, so I can enumerate it. So this is nothing but log of P of A comma B comma C comma D bar, and I'm going to ignore the theta, plus P of A comma B comma C bar comma D bar plus P of A comma B bar C D bar plus P of A comma B bar C bar D bar. Okay, so that's the expression for the log likelihood. We can now rewrite each one of these terms in terms of theta. So the first term is, I know that theta is equal to A, so all I'm going to do is like project this assignment on the Bayesian network and write down the terms. So this will be equal to log of theta A, right, because A is true, times theta B, because B is true, times theta of C given A comma B, so that parameter here, times theta of D bar given C. Okay, but we are never representing D bar given C because we are only representing D given C, right? So the last quantity will be equal to 1 minus theta of D given C. Agree? Okay. Similarly, I can compute the second quantity, which is theta of A again, theta of B, 1 minus theta of C given A comma B. Okay, because we have C bar times 1 minus theta of D given C bar. Okay, because we needed like D bar given C bar, plus theta of A again 1 minus theta of B, because we have B bar, right? Then we have theta of C given A comma B bar, and the final quantity is 1 minus theta of D given C. And then the last term, which is that guy, is theta of A times theta of, or I should say 1 minus theta of B, 1 minus theta of C given A comma B bar into 1 minus theta of D given C bar. Okay, so that's the expression for the log likelihood according to the data point that is given on the slide. Okay, so our task now is to compute the gradient of this with respect to the likelihood function, or I should say the gradient of the likelihood function with respect to each one of these parameters. Okay, so let's try to compute the gradient of this function. This is the log likelihood function for the data point with respect to, let's say, theta of D given C. Okay, so how will you compute that? So if I want to compute the gradient of this with respect to theta of D given C, I'm going to differentiate this expression with respect to theta of D given C, treating everything else as constant. Okay, so the derivative of this with respect to theta of D given C is 1 divided by So remember, derivative of log of f of x is equal to 1 divided by f of x times the derivative of f of x. Okay, so log of this whole expression, so derivative of the log of the whole expression is nothing but 1 divided by the expression, and actually the expression is equal to p of a comma d bar, right? So I'm going to write p of a comma d bar times derivative of this expression over here inside the brackets with respect to theta of d given c. Okay, so what is the derivative of that expression with respect to theta of d given c? Let's calculate that, right? So this will be equal to, so I'm just calculating this guy. The first term will be theta a, theta b, theta of c given ab. Okay, and the derivative of 1 minus theta of d given c is nothing but minus 1. Okay, what about the second expression? The second expression does not contain d given c at all. Okay, so that will be a constant, and so the derivative of that will be 0. Again, the third expression contains theta of d given c. Okay, so that will be theta of a 1 minus theta of b, theta of c given a comma b bar, and we have 1 minus theta of d given c, so the derivative of that is nothing but a minus 1. Okay, and the last expression again does not contain theta of d given c, so the derivative of that will be 0. Okay, so the derivative is negative in this case. It's equal to negative of the product of these three quantities plus the product of these three quantities. Great. Okay, so that will be the derivative with respect to theta of d given c. Similarly, you can compute the derivative of this expression with respect to theta of d given c bar, derivative with respect to theta of d bar given c bar, and so on. Okay, and actually we don't need the derivative with respect to d bar given c bar or with respect to d bar given c, and the reason is that they are nothing but 1 minus of, so for instance this guy over here is equal to 1 minus of theta of d given c. Similarly, theta of d bar given c bar is 1 minus of theta of d given c bar. Okay, so that's how you can solve this problem. Just write down the expression for the log likelihood and then just take the derivative of the log likelihood with respect to each one of those parameters. Okay, and then you're going to update the parameters using the gradient ascent algorithm. So it turns out that we can come up with general expressions for the gradient of log likelihood, and they are given on the slide. In general, the gradient of a data instance, which is represented by this O, with respect to CPT value, which is probability of x given u, is equal to 1 divided by probability of x given u times the joint probability of x, u, and the data point. Right? So if the data point is complete and it includes x and u, then this probability will be equal to a 1. If the data point is incomplete, right, then we are just going to make sure that the data point is consistent with x comma u, and if x, any one of these x or u are missing, then we are just going to take the product of those respective probabilities. Okay, for the data set in general, so this is just for one point or one example, and if you have a data set with multiple points, so in this case let's say m examples, then the derivative is given by 1 divided by probability of x given u, remember x given u is our parameter, times the sum over all the examples of the joint probability of x and u given the data point. Okay, so the sufficient statistics here again, as you can see, is probability of x comma u given the data point same as the EM algorithm. So technically, we can use inference procedures such as the junction tree algorithm to compute these sufficient statistics. And the same problems that we had in the context of the EM algorithm will remain here. So if you remember, our problems were that if the tree width of the Bayesian network given these observations is large, or if the Bayesian network does not have context specific structure and all these other nice things that we require for inference to be tractable, this gradient descent or gradient ascent algorithm will be impractical. Okay? And we'll have to resort to approximate inference algorithms to compute the gradients. And typically when gradients are computed using approximate inference algorithms, we don't have guarantees that we will reach the local maxima of the likelihood function. Okay, so the same problems as EM, it's just an alternative algorithm for computing the or getting as close as possible, I should say in this case, to the local maxima. Okay, so that completes our discussion of parameter learning algorithms for Bayesian network under the assumption that you have partially observed data set, right? And we are going to use the, we were using, I should say, the maximum likelihood estimation criteria, okay? So one question that I often get is when to use gradient ascent versus when to use the EM algorithm. So this is more of an anecdotal knowledge and not based on sound theory, but in practice what people have found out is that EM takes somewhat larger time to converge as compared to the gradient descent algorithm. And typically the way EM works is that if it will take a very large step if you're farther away from the optima, but as you get closer and closer to the optima, in this case local optima, EM will be very, very slow. So to draw something or to illustrate it on using a drawing, what I want to say is that let's say this is your likelihood function and let's say you start somewhere here. So what EM will do is that initially it will take like very large steps. So maybe after 10 iterations or so you'll be here, right? And maybe after 53 iterations or so you'll be somewhere over there. But in order to reach this maxima, this local maxima, EM might take another 100,000 steps, right? From this point to that maxima point, while it will get to a point which is close to the maxima in something like 100 to 200 steps. Okay, so if you're very far away, EM takes really nice jumps. Okay, but when we are very close to the optima, EM takes like very, very slow jumps. On the other hand, gradient descent or gradient ascent in this case, I should say, always call it gradient descent because typically in practice we always have minimization problems. So that's why you will hear me talk about gradient descent all the time rather than talking about gradient ascent. But every time I talk about gradient descent, think of it as I'm mentioning gradient ascent because we are maximizing it and not minimizing here. Okay, so gradient ascent, what it will do is typically it will be very slow when you start from a point which is far away from the optima. Okay. However, when it's near the optima, it's typically faster than the EM. Okay. So that's why sometimes what people will do is they will run EM for some iterations. Take the solution, right? Stop EM, take the solution and feed it to the gradient ascent algorithm and let the gradient ascent algorithm do the work after that. Okay, and this is based on anecdotal knowledge or the way we have implemented these algorithms so far, and there is no sound theoretical basis for this. Okay. Second thing that I want to mention is that EM is a more general algorithm than gradient ascent, because gradient ascent requires that the function be differentiable. EM does not require that. Okay, so in certain cases, if you're trying to solve a maximization problem in the context of partially observed data, and it turns out that the objective function that you're using, so in this case you're using the log likelihood as the objective function, but had you used some different type of objective function, maybe that the objective function was not differentiable, then gradient ascent cannot be used. And what you'll have to do is use the EM algorithm. Okay, so that concludes our discussion of EM and gradient ascent. And if you have any questions, ask them on Piazza, and we'll have a class on Tuesday where we'll discuss them.